Okay, so today we're going to be talking about two neuron circuits. The first one we're going to be talking about is the excitatory circuit. So, in the excitatory circuit, we're going to start with this first cell. We're going to call it the Go cell. The first cell in both of these circuits is going to be called the Go cell. It's going to contain this neurotransmitter known as glutamate, shown here in pink. It's trapped in these little vesicles and will be diffused across that membrane. It's going to attach to these receptors shown here in black. These are called the AMPA receptors. These are the primary ionotropic glutamate receptors, and glutamate is an excitatory neurotransmitter. It's the primary one in the nervous system. Now, when the glutamate binds those AMPA receptors, what's going to happen is sodium, here shown in red, is going to rush into the cell. And it's going to have a plus next to it showing a positive charge, which means the membrane potential is going to become less negative inside the cell. And that is going to be counted and summated here at the axon hillock. And if it reaches a threshold at negative 55 millivolts approximately, then that signal will continue to propagate down the ion, causing the adjacent sodium ion channels, which are voltage gated, to open up. Now, following that, shown here in purple, are going to be these potassium channels. These are also voltage gated, which will cause potassium to go out of the cell, and this will ultimately balance it out, so then that membrane can stay at a negative resting state. And with the various channels down the axon, it will allow the signal to maintain strong because it will form kind of a new wave like dominoes falling. Now, by the time it gets to the end of this terminal, because it's excitatory, there's going to be more glutamate receptors, more glutamate neurotransmitters. And the way that these are then released across the synaptic cleft is through calcium, which is going to be shown here in dark purple. It happens that the calcium will bind onto something called synaptotagmin. And the synaptotagmin is a protein, and the calcium then allows that vesicle to bind to the cell membrane, and the neurotransmitter then diffuses across the cleft, attaches onto those AMPA receptors, onto that third cell, and hopefully, if reaches threshold, this excitatory circuit will continue with that same sodium-potassium cycle, and that will just drive the excitatory signal forward. Now, second, in the inhibitory circuit. Now, in the inhibitory circuit, again, we are going to start with this first Go cell. It's going to still have that glutamate, that excitatory neurotransmitter, which will ultimately bind to those AMPA receptors and cause the sodium influx and that depolarization that we talked about before, which is that big increase on that graph that you can see up at the top of the paper. Now, once that threshold is reached and those sodium channels open and the delayed voltage-gated potassium channels open, we're going to reach the end of that cell at that presynaptic terminal. Now, instead of glutamate at this presynaptic terminal, because it is inhibitory, we're going to see here, I'm going to draw in green, it's going to be GABA, which is the primary inhibitory neurotransmitter in the nervous system. Now, GABA, just like before, with that help of the calcium, is going to bind to that cell membrane and diffuse through exocytosis across that synaptic cleft. And it's going to bind again, but not to AMPA receptors, but instead it's going to bind to something called a GABA A receptor. And what these GABA A receptors are going to do is they are going to then cause chloride, which is a negative ion, to flow into the cell. And this is then going to make the membrane potential more negative than usual. And that's going to be shown in blue. And why making it more negative is important is because this is what causes it to be inhibitory. So as you can see, this downward space on the graph, that's called hyperpolarization, which is driving the membrane potential farther away from threshold, which is making the action potential less likely, which is why it is called an inhibitory, because it will effectively silence that third cell and no action potential will be fired because there's no ions moving into the cell.